Okay. So yeah, we'll read it out as they come in. So yeah, so a typical electrolyzer is going to consist of these following key elements. So it will consist of an electrolyte. You'll have an electrolyte, and you'll have a cathode, and you'll have an anode. So okay, I think we've got a bit of a lag. So we've got people from Huddersfield, Germany, another person from Germany, we've got United Kingdom, and we'll continue. I think there's a bit of a lag with the chat here that I'm seeing on my end. So yeah, so we've got the electrolyte membrane. So in PEM electrolysis, you don't have to actually have an electrolyte mixed in the water. So in alkaline, you have an electrolyte mixed in the water. It's normally going to be potassium hydroxide or sodium hydroxide, and that is going to be your electrolyte, and that electrolyte is going to be normally around 25-35% concentration in the water. And in electrolysis, your membrane itself is the actual electrolyte. So it's made out of this polymer material. That's why it's called polymer electrolyte membrane. It's made out of this polymer material, which is actually the electrolyte itself. So what you get to do with PEM electrolysis is you just run water onto the anode side, and when you decide to add the electricity, the reaction will start to happen, and you're going to have the oxygen evolution reaction, hydrogen evolution reaction. So the oxygen evolution reaction will cause you to have oxygen bubbles forming on the anode side, and the hydrogen evolution reaction will cause you to have the hydrogen bubbles forming on the other side of the membrane. That is when DC current is applied and the threshold voltage is reached. And by the way, the threshold voltage in thermoneutral electrolysis, so real life electrolysis, real life PEM electrolysis, is going to be around 1.48 volts. Theoretical thermoneutral not thermoneutral, sorry, the theoretical minimum voltage for electrolysis is going to be 1.229 volts or 1.23 volts. So that can kind of only be achieved in the lab at a very low production rate, and we'll go into that shortly. But the electrolyzers are run at around 1.822 or up to about 2.2 volts per cell. And we'll look at the components here quickly. So we have the MEA. So the MEA stands for membrane electrical assembly, and that is going to be your membrane. It's going to be the catalyst either side. So on the anode side, which is the oxygen side, you're going to have iridium oxide as a catalyst, and you're going to have platinum catalyst on the cathode side. You're going to have this porous titanium. So this can be a sinter, or it can also be a felt. Sinter is a powder material being compressed. So it's titanium powder material, and what it is basically it looks like a just a normal plate of titanium. However, it looks and feels very, very porous. And when you actually pour water on it, instead of the water just running off it, the water just goes right through, because it's just so porous. It's able to allow the water to go right through it. And then you have the titanium meshes, and together the titanium mesh and the porous titanium make up the PTL, the porous transport layer, or the gas diffusion layer. And this is going to be on both sides of the MEA. And you've got to have a sealant, which goes around the actual cell, which is going to be normally the thickness of the porous transport layer on both sides. So you're going to have a sealant on the anode side, and you're also going to have a sealant on the cathode side. So this is just one cell, though, and if you stack several cells on top of one another, then what you're going to have is a stack. And a lot of larger stacks today, industry standard sort of megawatt scale stacks, are going to have around 80 to 100 cells, sometimes more, sometimes a little bit less. And um, the cells are actually divided uh, by the bipolar plate. The reason the bipolar plate is called the bipolar plate is because the bipolar plate on one side of the bipolar plate there is nothing, on the other side of the bipolar plate is going to be the cathode for the next cell. And we'll look at it from a slightly different angle. So you've got the two end plates, and then in between the two end plates you have the membrane, the MEA. You've got the porous transport layer on both sides, and again, this is just one cell. But if you were to squeeze in a lot more cells in between these two end plates, then you would have a stack of many cells. And so the same sort of thing over here. So you've got the membrane, you've got the porous transport layer. So you have the titanium sinter, you have the mesh, and on both sides you have the same. And then you have here the cell, whatever you want, whatever you want to call these. You can call these cell plates. You can call these this sealant. And normally there's some sort of a gasket in between them as well. Although not in all systems. And so I'd like to go and show you what actually happens in the cell. So you have water go into the cell, and if you want to imagine this, this is going to be one cell, and the water is going to go in here. This is going to be the anode chamber. This is going to be the cathode chamber. You've got the PEM membrane, and a lot of people ask, PEM, what does that stand for? It stands for two things: polymer electrolyte membrane, and it happens to be PEM also happens to be the acronym for something else, which is the proton exchange membrane. And they're essentially talking about the same thing. Is this membrane, this green labeled membrane here? But the only difference is that polymer electrolyte membrane definition, it tells you what material is made out of, and that it's actually an electrolyte. Proton exchange membrane tells you that what the proton exchange membrane tells you is that it actually conducts protons. It allows the protons to go through, whereas in the traditional sense, this PEM membrane, in the traditional electrical sense, it's actually an insulator because it doesn't allow electrons to go through, but it does allow protons to go through. So it does exchange protons. So here's what happens. And I'm just trying to keep an eye on my time here. Here's what happens. So you have the water go into the anode chamber, and let's just talk about electrolysis here. So the water actually goes through the gas diffusion layer. So these two layers do the gas diffusion layer. The water goes onto the surface of the membrane, and when you switch on your PSU, you are going to apply a positive onto the anode side, and you're going to apply a negative to the cathode side of the membrane. And what you'll have, well, the reaction is going to happen. And what that means is you have, this is the hydrogen atom here. So your hydrogen atom consists of one electron, one proton. So the proton and the electron are going to split once you reach your threshold voltage. And that after you've reached the threshold voltage of 1.48 volts, the first reaction is going to happen. So that's the minimum voltage to split one electron off the proton. The electron is going to actually go through the electrical connections over to the other side of the cell. And when you're talking about the stack, it gets a little bit more complicated than this, but basically, essentially what happens is that instead of the cell going, instead of the electron going through the power supply, it actually just goes through the bipolar plate over to the next cathode. But we don't have time. We don't have a lot of time to go into that right now. So the electron is going to go through the electrical connections over to the other side of the membrane, and the proton is now going to be so tiny, because the proton and electron, that's the hydrogen atom, that's like relatively big. Even though it's small, it's like relatively big. But the Proton just by itself is just extremely, extremely, extremely tiny, and this proton is actually now so tiny that it's actually able to go through the PEM membrane. So it's going to go over to the PEM membrane. Because the proton is positively charged, it's going to be propelled by the positively charged anode over to the cathode side, which is attracting it because it's negatively charged. So the proton will want to go through through the PEM membrane. And like I said, the electrical connections, the electron, what is the flow of current? Current is the flow of electron, right? So that's how the electron is actually able to go through the electrical connections. And guess what? When they go to the other side, the proton meets the electron, and they'll join up, and they'll form a hydrogen atom, and they beautifully join together, and two hydrogen atoms is immediately going to form an H2 molecule, and there you go. That's the electrolysis process there in a nutshell. A few other things are going to happen as well. We'll come back to this arrow, but a few other things are going to happen. So during electrolysis, what you'll have is what's called electroosmosis, and you'll have which is a component of water transport. And what you'll have is this PEM membrane is the barrier between the anode and the cathode side. However, the PEM membrane has to be the PEM membrane also, by electroosmosis, allows some water to be attracted through with the force that is exerted on it during electrolysis. So there is a force pulling water through, which is directly proportional to the generation, or to the hydrogen generation, or the current density. And essentially, the more hydrogen you're generating, the more water you're also taking over or attracting over to the cathode side. It's perfectly normal during PEM electrolysis. Another thing that is going to happen is this is represented by this arrow here. So that's going to be fusion. And what that is the fusion happens regardless of whether we're electrolyzing or not, because it's only dependent on whether or not there is water being flushed through the anode chamber or not. So if there's water in the anode chamber, the way this PEM membrane is made is that PEM membrane won't do anything. It won't generate any hydrogen for you if it's dry, because the PEM membrane only works when it's wet. It has to be hydrated. So the PEM membrane, you can almost imagine the PEM membrane to be a sponge. So when you are putting water on one side of the sponge will soak and the water will come out on the other side of the sponge. So that's how I'd imagine the PEM membrane. So when you apply water on one side of the sponge, you eventually are going to have water coming out on the other side of the sponge. So this happens regardless of generation. This happens whenever your main circulation pump is running. So there is one last arrow here which I'd like to talk about, and this is hydrogen going back onto the anode chamber. So there is going to be a pressure gradient, and the pressure gradient is normally in most systems going to be 30 bars, and the cathode side, the hydrogen side, is going to be pressurized to around 30 bars or 35 bars on most systems, most modern industry standard PEM electrolyzers. And the anode chamber is going to be very close to atmospheric. And because of this pressure gradient, the hydrogen will want to go back. The PEM membrane is just normal. It's pretty normal, and it's just normal operation. The way that the PEM membrane works is that it will allow some hydrogen back, and this flow of hydrogen back is going to depend on the magnitude of the pressure gradient. So the bigger the pressure difference, the higher the transport of hydrogen back. Now, there's another concept that I'll just quickly explain. It's quite difficult to explain it in a very short amount of time, but essentially what happens is when you have hydrogen going back into the anode chamber, you are going to have a problem. Hydrogen It's a flammable substance. It's explosive. When you're mixing it with an oxidizing substance, especially you're mixing it with oxygen, pure oxygen, uh, you can have a very serious situation on your hand. And um, the lower explosive limit for hydrogen in air and hydrogen in oxygen is 4%. The upper explosive limit is 75% in hydrogen and 94% in hydrogen and oxygen, pure hydrogen and pure oxygen. But the lower explosive limit is still going to be 4%. So here's the thing. If I'm putting hydrogen into the anode chamber, I'm actually going to get quite close to that 4%, and I want to get as far as the 4% as possible because I do not want to reach the 4% explosive limit. Now, the way I can overcome this is if I make sure that I'm generating enough, because what happens is on the oxygen side, you are going to have the oxygen evolution reaction, and therefore I'm generating oxygen on the oxygen side. And I want to make sure I'm generating enough oxygen to dilute this relatively small amount of hydrogen to make it even smaller in percentage in this oxygen stream. And essentially, I'm just wanting to make enough oxygen to go with the hydrogen that's going back onto the anode side. Okay, so we have we're going to talk about the membrane here. So the membrane itself is a perfluorosulfonic acid polymer, and it basically has this acidic sort of property which allows it to be the electrolyte. And generally, the industry, the PEM membranes used in large scale electrolysis are going to be around 80 to 200 microns, so they are very, very thin. Main brands are the following. So most electrolyzer manufacturers would use one of these electrolyzer brands, and DuPont, very famous one. There you've got the old Nafion M115. That has a thickness of 125 micrometers, 125 microns. Also the much less used these days, Nafion N117, for example, which is much thicker. I believe it's 175 micrometers. So it's quite thick membrane. So thinner the membrane, typically, the more efficient. However, also the thinner the membrane, also the less durable typically, and the higher the rate of crossover. So there's the Gore PEM membranes also. It's the M275.80. That's an 80 micron thick PEM membrane. And you have the Johnson Matty one, which is just made about an hour up the road from where I live. And those are that's also a well-established company that's manufacturing membranes. And then you've got the various more recent startups. These are especially China. Yeah. Okay. So on to the MEA. So a lot of people are asking, what is the MEA? What is the membrane electrode assembly? So here's the thing. A lot of people refer to the MEA being different things. So I've spoken to people from Canada, from the US, from Germany, from all of the world, and like a lot of people tend to have a different idea of what the MEA is. But most people would agree that the MEA is the PEM membrane, and it also includes the anode and cathode catalyst. So it's basically the PEM membrane, and it has the anode and catalyst loadings on both sides. But I've also heard, that this is what most people are going to refer to, but some other people you might hear referring to the MEA, and what they actually mean is the PEM membrane catalyst on both sides, plus the porous transport layer. Um, and essentially, what they're referring to is like pretty much an entire cell. Um, so yeah, just as way of information, if you hear mem- membrane electrode assembly MEA, doesn't it doesn't really have a specific definition. So for stacks, the next thing I'd like to talk about is degradation mechanisms. So in this is quite important. This is it's quite a hot topic these days. Um, the degradation mechanisms for stacks. Why are stacks failing? Why are they uh, why do they keep failing more often than a lot of people hope? And so essentially, you can kind of attribute it to about three things. And one of them is membrane thinning, which is caused by hotspot formation. And the other one is the catalyst loading, and number three is going to be the increase the voltage, the increase in voltage for end of life, and the end of life voltage being reached before end of life should come. So let's talk about these one by one. So low water flow, and so this is very difficult because when you're designing a stack with 100 cells, or when you're designing a stack of 50, 60, 70, 80, 90 cells or even more, you run into an issue where you run into a mass transport issue. So the water, are you actually able to pump all of that water that stack needs with the pumps that you have and the pumps that are available, or or not, essentially. And if you don't have enough water flow in a stack, what you'll have is hotspot formation, and these are literally hotspots. These are going to be areas of your membrane where, if I go back quickly to my membrane diagram here, on the oxygen side, you are going to have, so let's say this is the surface of the membrane. You're going to have on the surface of the membrane oxygen, forming oxygen bubbles. Now, these oxygen bubbles are forming faster if you increase the current density. So when you crank up the current density, these bubbles are flowing, these bubbles are forming. And are you able to have the water flow sufficient to wash wash these oxygen bubbles away from the anode chamber? Because if you don't, then you're going to have extra hotspot formation, and you're going to basically on these particular areas there's no electrolysis. It's going to reduce, just not going basically electrolysis in these spots where you have oxygen is just not going to happen. There won't be any electrolysis whatsoever. It's not that the efficiency will go down. There just won't be any electrolysis on those spots. But what there will be is frying of the membrane for a split second. And if you just keep on frying it for split seconds over and over again, then eventually you are going to achieve membrane thinning. This is terrible. When you have membrane thinning, you basically are frying bits and parts of your membrane. You are eventually what you'll have is you'll have tiny holes in the membrane, and you are going to increase your crossover rate. So um, your hydrogen, like we said before, because of the pressure gradient, you'll have more hydrogen coming back into the anode chamber, which can be which can lead to explosions. And second is also it's relatively similar. So if you design stacks which prevent water flow from going through to actually reaching the membrane easily. So if for example, your porous transport layer is way too thick, or not very porous, if your porous transport layer isn't even like that porous as it should be, then the water isn't able to wash away those oxygen molecules. And um, um, the next degradation mechanism that we're going to talk about is the substandard water quality, and uh, this is the big thing. So um, it really shouldn't be, and we keep on hearing, um, that water quality isn't water quality should not be an issue. The project water quality and the water purification system is about 1%, 1 to 2% of the cost of the entire electrolyzer. So you're definitely not going to save any cost on that. So uh, we must make sure. I can't even emphasize enough. We must make sure that water purity is sufficient um, for the stack. And what you also have to make sure is, so number one, your water purity and the water purity that you theoretically are able to achieve is 0.056 microsiemens per centimeter. You can't really get any better than this. You can't really get any better than 0.056 microsiemens per centimeter. But this is the water conductivity coming straight out of the water purification system. It doesn't mean that this is the water that's actually going through the stack, because um, this you're going to you're going to have all kinds of rubbish wash in from the stack. So when you're electrolyzing by electrolysis itself, um, the system is going to generate a lot of essentially a lot of chemicals that you then need to polish the water for. And um, you basically the like what you can easily achieve with a great water purification system is 0.5 microsieverts per centimeter conductivity, and this is the actual water conductivity that's going through the stack itself. So you can achieve that by running around 5 to 10% of the. Some people talk about one, even as low as 1%. I disagree with that. I think you need to go up at least 5%. Of the water that's actually going through the stack, and just this whatever stream. So let's say you have 1,000 liters per minute of water going through the stack. Um, you should have about 5% of that um, uh, running through a water polishing circuit. So that's going to be either EDI or it's going to be a mixed bed resin. By the way, EDI is a relatively new addition to the PEM electrolysis systems, and for larger systems. Well, for larger systems, most vendors would have an EDI. This is electrodeionization. So yeah, cannot underemphasize the water conductivity. And last but not least, the low catalyst loading. So a lot of vendors are boasting about how low their catalyst loading is, but when the stack fails prematurely, that doesn't look that good as it did initially. So especially on the anode side. So on the anode side is where we have really care about the water. Sorry, not the water. The catalyst loading is on the anode side is where we care about the most, because the oxygen evolution reaction takes up the most amount of energy compared to the hydrogen evolution reaction, which doesn't really take that much energy. But the oxygen evolution reaction um, is going to this is where we want to have um, the catalyst loading, and just where we want to make sure that the catalyst loading is definitely sufficient. And there's a lot of research going into building new catalysts, and using less of the iridium oxide, which is extremely expensive, and using um, newer and more modern electrolyte, using more modern catalyst material into electrolyte membrane. Okay, so Um, so next up, we have the IV characteristics. So this kind of goes hand in hand with end of life because essentially the higher the voltage. So let's say you run the stack at 3 amps per square centimeter. At beginning of life, at start of life, you are going to have so this graph is showing you that at 3 amps per square centimeter, you start of life, you're going to have a voltage of 1.8 volts um, at 3 amps per square centimeter. However, um, there is a tendency for this voltage to increase, to go up over time. So after the first year, second year, up to 10 years, the stack should last for 10 years. Um, and in that time, the voltage is slowly going to creep up, where you're having to put in more energy into the same stack to get less hydrogen out of it, essentially. And that this you know uh, developing of this inefficiency that you are going to see at older stack designs. If you have a look, um, is going to be reduced if you are passing um, um, high quality, very low conductivity water through the stack, and you're electrolyzing with water um, that's very pure. Okay, so yeah, just a couple of things on efficiencies. So um, it normally takes about 55 kilowatt hours of electricity to produce 1 kilogram of hydrogen, and it's very common to have a 10% balance of plant as of that on um, on large scale electrolyzers, and 1 ton of hydrogen is then of course going to mean that it takes around 60,000 kilowatt hours to generate 1 ton of hydrogen with a PEM electrolyzer. So, and like I said, as we're reaching end of life, this output is going to reduce because the efficiency is reducing, the voltage efficiency is reducing. So, when we talk about degradation mechanisms, there is a company called Weidmuller who has a great device which essentially is a probe for a lot of the cells within your stack, and it runs a lot of measurement and finds a lot of data of the stack. And this stack is well, when you have a stack failure, for example, you're actually um, you're actually going to have way more data when you have a stack failure, because this wide model system is able to tell you the voltage across each of the cells, and from that you can just run a multitude of you can just get a multitude of data. You can get a ridiculous amount of data, and if you so there's also there's also a lot of research going into getting this system ready to also tell you which cell has failed. If you have a stack failure, it will tell you which cell has actually failed. So you don't have to take the whole stack apart. You can just dig down to that particular cell and fix that particular cell. The stacks are extremely expensive, both to build, but they're also really expensive even to fix if even to rebuild when you have a stack failure. Okay. Um, so we're almost coming to an end for this webinar today. I just have a few more slides. I think I have about 3 or 4 more slides, um, but I'll try to hurry up. So oxygen management. So And this is really interesting. So when you're generating hydrogen, you're also generating oxygen, and I'm talking about the anode side right now. So on the anode side, you're going to generate quite a lot of oxygen. And if you look at this diagram down here on the right, let's say you have a 1 megawatt stack and you're running running 1,000 liters of water across your 1 megawatt stack. Well, this 100% is 1,000 liters. Out of that, when you're running the stack at 3 amps per square centimeter, you're going to lose about 0.2% of the water. Because, by the way, a lot of a lot of people think that when the water that you're running into the stack is going to get all used up and it's all turned into hydrogen and oxygen. No, no. You're running that water through the stack, and some of it, a small amount of that water is going to turn into hydrogen and oxygen. But most of the water is just running through the stack and is used for washing away all the chemicals and also to cool down the stack because especially on the anode side there's a lot of essentially inefficiencies essentially um, which are which is going to cause heating, and that heat has to be um, that heat so the water is used to transport the heat away from the cell to as to not damage the membrane. So um, yeah, so coming back to this diagram, we have about 1,000 liters of water go into the stack, and a very small amount of water is actually going to get used up. So it's only about 0.2% of the water biomass is used up, and 99.8% of the water is going to come out of the stack compared to what went in. However, if you look at it by volume, you've you have an increase of around 38% in in the volume because of all the oxygen that you've generated. So this is the oxygen coming out of the stack. So the volume here coming out of the stack is going to be just a massive, massive volume. Now, just think of it this way for a second. So when you're running at small current density, you're generating less oxygen, or the water is flowing through the stack with a smaller resistance. It's easier to push through water across the stack when your current density is low. However, when you're actually increasing the current density, you're also generating more oxygen. Therefore, you're also increasing the resistance of these fluids across the stack and from the pipelines coming out of the stack. So because of that, the if you're running the water pump at a constant rate at lower current density, an actual large scale electrolyzer, if you've actually seen a large scale electrolyzer work, when you're running the water pump at the same output, so let's say you're running your water pump at 90%, um, you are at low current density, you might reach your 1,000 liters per. But at high current density, when you actually need that bloody water to go through the stack, your your resistance goes up, therefore your water flow at the same rate at the same uh, the same effort of the pump, your water flow is actually going to reduce, and that reduction in the water flow can be substantial. And we're going to jump over to these last couple of slides, and essentially, to wrap to sum it up, we can achieve basically we can achieve great efficiency. However, you're going to sacrifice a few things. So you can either achieve your great efficiency, you're going to sacrifice your apex or your capex or your opex. And also, if you're going to have a massive durability, you'll use your thicker membranes. You're going to use you're going to increase your catalyst loading, etc. Yeah, that's going to be quite expensive. So yeah, you want to you want to find a sweet spot, and that's what a lot of electrolyzer manufacturers are trying to do today. They're trying to find a sweet spot, and yeah, a lot of it is working, a lot of it is not. I've said, and just to sum it up, final slide. Just wanted to just point out that this over here is a stack component. So this is the actual just all the bits for the stack. And by the way, most of these can be reduced, especially on, on the membrane side. Um, so catalyst side today, it's very difficult to reduce to reduce the catalyst loading. Iridium is insanely expensive. Iridium is more than 3 times the cost of gold per kilogram. Iridium is extremely expensive. There's a lot of organizations that are looking into improving the um, well, basically having an improved catalyst which doesn't cost us as much, and it also has the same durability. So ruthenium, for example, there's like ruthenium is actually it's interesting because ruthenium is actually even a better catalyst than iridium, and it's cheaper and it's more reactive, and you can make more efficient stacks. However, it can't really last for a very long time in that highly oxidizing environment. Hence, we use iridium. But hey ho, and another thing that we can massively reduce the cost for is what you see here, 9%. This is the most expensive part of the power supply. This is around 30%, one third almost of the cost of full electrolyzer systems, and this doesn't even include uh, um, it doesn't even include the transformer. This is just the power supply unit, excluding the transformer. It's 29%. So I've done a bit of thinking into this one actually, and into quite a lot of them. But just to give you a bit of background to this, this to me it doesn't seem like these power supply units are actually worth that much. It's also if you ask for a 3.5 to 5 megawatt power supply unit, is going people companies are going to quote to you between 200,000 pounds, 300,000 pounds, um, and sometimes even more for these power supply units. But you know what? These I was trying to figure out where why is it so expensive essentially? Why are these power supply units so incredibly expensive? And it's definitely not the copper that they put into it. Let's put it that way. It's definitely not all the raw materials that they put into it. If you look at it from first principles perspective, these should be much cheaper. And really, what most electrical and electronics engineer would agree on is that